This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Good afternoon. So we started a MOS transistor in the last lecture. So today we are going to look at the channel potential variation. So we are going to look at the potential difference across the channel between source and the drain. So as we discussed, if you are operating your MOS transistor in the triode region, then what you will find is here you can see as a resistor, the value is depending upon the voltage you applied to the gate. So it's basically a voltage dependent resistor if you are operating your MOS transistor in the triode region. So then now we are going to find out the potential variation across the channel, across this channel. Here this is a VG. Then here when you connect voltage, what is happening is depending upon if it is positive, then you will be getting positive charges here. And then because you are operating in the triode region, then the potential difference across this region is different because of this resistance variation. So what I want to explain is, see, this is VG. And then here you will be getting VG. Then VG with respect to this point is different. VG respect to this point is different. VG respect to this point is different. So how it will be varying is if you are plotting the voltage across these two regions, see the source region and drain region, then what you will find is something like this. The voltage is increasing. Means you see that Vx, that is a voltage at any point. So you got VD here, and then this side you got a voltage, but then this side you don't have voltage because this is grounded. So that is the reason here you see very small 0 voltage. Here you definitely see 0 voltage, but then across the resistance you can see the voltage is increasing, and then this point is equivalent of this point. That is your VD. So that is the reason we are getting something like this. See, slowly it is increasing. Then this is a voltage across the channel, this channel. Now what we are plotting is a gate substrate potential difference. So voltage at the gate with respect to each point in the channel. Voltage between this point, voltage between this point and this point, voltage between means gate and this point, voltage between gas and the drain. So we are going to plot it. So if you are plotting, then what you will find is voltage between gate and this point is higher because this point is grounded. So that is the reason here you see very high voltage here. And then voltage between gate and this point, your drain is lower. Why? Because you are only getting a positive charge here, positive voltage here, so that this difference is small. So when I put in some values, it will make clear. So suppose this is 2 volt. If we connect gate 2 volt, then what will happen is all this point across this line, this is metallic or it's a conducting plate, you will get 2 volt. Now, if I connected VDS, so this 2 volt we are applying with respect to this ground and then this ground. Again, I am going to connect this VD 1 volt. Again, that 1 volt is this voltage 1 volt is with respect to this ground and this ground. And then my question is, what is this voltage? The point here. Okay, 1 volt. Definitely that will be 1 volt. Why? Because you connected here 1 volt, then this is a resistance, then that is connected to the ground. So then you will be getting 1 volt. Means here what you have seen is see you are connecting 1 volt here. So this is my 1 volt, and then you have got a resistance. Yeah, sorry, I think I will focus it. Yep. Yeah, so then if you connect 1 volt, so this is 1 volt. So this is 1 volt, and then this is the resistance. And then what I am plotting is what is the voltage across this resistance. That is our channel. Definitely this point will be 0 because this is ground. So that is the reason here it will be more, and then towards this point it is 1 volt. See? And then if I measure this point with respect to this ground middle point, you get 0.5 volt. So that is the reason here is 0.5 volt. So this is the distance x. So this is the distance x. So that's what, sorry, this is the distance x is up to here. This is x, this length. That is L, and then this length is L. So across the resistance, because this is grounded, this is 0, and then it is coming here, you are getting 1 volt. That's what we are getting here on the screen, here 1 volt. Then in the next one, what we have plotted is, you can see gate substrate potential difference. So what do you mean by gate substrate? Now we are going to see, you have connected 2 volt here, and then we are going to find this 2 volt, what is the voltage between gate and each point in the channel. Like this point and this point, what is the potential difference? This point and this point, what is the voltage? This point and this point, what is the voltage? So my question is voltage between this point, the gate and maybe this part, what is the voltage? Between gate and this part, what is the voltage? Definitely that is 2 volt, because here you got 2 volt, you are measuring with respect to ground, you are getting 2 volt. Then between gate and drain, this point, what is the voltage? The voltage between voltage between this gate and this point here, what is the voltage? 1 voltage. Why? Because here you already got 1 volt. So 2 minus 1, 1 volt. See, now you can see the voltage between gate and source is different when you compare it to gate and drain. Both are not same, not 2 volt. So this voltage is 2 volt, but then this voltage is actually 1 volt, and hence here, when it comes here, you are getting around 0.5, maybe 1.5 volt is the voltage between gate and the middle point. See, then when you apply a 2 volt to the gate, actually what is happening is across this channel, the voltage is not the same. So that's what we have plotted here. Gate substrate potential difference. So that is Vg. Yes, Vg is equal to 2 volt with respect to this point. So this point voltage is I plotted here. And then what will happen is that gate substrate voltage is decreasing across here, and the minimum value is at this point. That is equal to 2 minus 1, you are getting 1 volt. So that is Vd minus Vg. So that will be 2 volt, and this will be 1 volt. Sorry? Yeah, so that is Vg minus Vd. So yeah, that is correct. So this is, there's a mistake. That's Vg minus Vd. Yeah, that's true. But then one thing is there, better to take the modulus. Sometimes you may connect the Vd a higher value. So the best way to write is, now I have connected 1 volt, but then when you are operating in the saturation region, your Vd will be usually larger value. And then you may get a negative. So better I would say Vg minus Vd is correct here, but then we will put maybe a modulus. Since there is a channel resistance between drain and source, see, that's what you see here. And if drain is biased higher than the source, yes, drain is biased higher than the source. See, this is a source, this is a drain. Channel potential increases from source to drain, from here to here. That's what this increment. And the potential between gate and the channel will decrease from source to drain. See, that is decreasing like this. So then there is a property called, or phenomena called pinch off. Maybe the phenomena, that is the correct word. Pinch off means here, why I have drawn electrons like this? Why there is a slope here? Can anyone please tell me why there is a slope? Because this is electron concentration, but now I haven't drawn it as a flat line. or a parallel line like this. It's not flat. Why there is a slope here in the electron concentration? So if you come back here in your previous slide, you can see the electron accumulation is depending upon the voltage here. And then this point, you know what I meant? Then here you are getting a higher voltage with respect to gate. Means here you are getting a higher potential. But then towards here you are getting a lower voltage. See here will say 1 volt. So that's the reason maybe I should draw it. So when you have your MOS here, so this is your gate, and then this is your oxide layer, and then here, so I have connected 2 volt. Then what is happening is this is your channel, and then this is your drain, and this is your source. Then this I have grounded, and then so this is a channel region, and then here I have connected maybe 1 volt. Okay. So when I do this one, see here 2 volt, then what will happen? Here so many positive charges are here, 2 volt. And then you got the oxide here, that is your insulating layer, oxide layer. So this is the oxide layer. Oxide layer. Then what will happen is this point it is 2 volt, and then voltage at this point, what is the voltage at this point? Here you are experiencing actually 2 volt. Then you have more electrons here. But this point, what is the voltage? Between gate and drain, what is the voltage here? So here 1 volt. So you don't have much electrons here compared to this region, because here you got a full 2 voltage between this point and this point. You know what I meant? So here you have more electrons accumulating, but the electron accumulation will decrease this region, because here you don't have that much potential difference between here, because you have connected a 1 volt here. You know what I meant? Then if I connect a 2 volt here, what will happen? What is the voltage between this point and this point? Then you will get a 0. See, electron concentration will be 0 here. You don't have any concentration. So that is the reason we have made a slope here in the electron concentration is different actually. You don't get across uniform. See, that is the reason here you got 2 volt, but then here the voltage is, the potential difference between gate and the channel is less here, because you have connected a positive charge here. That is the reason here you are getting a slope in the electron concentration. In the slope in the electron concentration here. So then here VDS, voltage between drain and source. So whenever we write VDS means VD minus VS, voltage at drain minus voltage at the source. That is less than VGS minus VTH. So that is how one. So now we are going to study one phenomena called a channel pinch-off. When we study the channel pinch-off, we are going to take into account different voltages, like a voltage between drain and source, which is less than VGS minus VTH. VGS is a voltage between gate and source minus threshold voltage in one case. Another case may be equal to, or we are going to greater than. So we are going to vary the voltages, and then we are going to study one phenomena called channel pinch-off. Why we are studying is we already found out the electron density is different across the channel. And then now we are going to find out some interesting phenomena because of this electron density variation across the channel. So I am going to put in VTH 0.5 volt to 500 millivolt. Means if you are operating below 500 millivolt, then your MOS transistor is off. So now it is above 0.5 volt. So your VTH is 0.5 volt. Then, as I said, I will take another condition, VDS equal to VGS minus VTH. Then I also will take another condition, VDS greater than VGS minus VTH. So these are the 3 conditions we are going to study. And then first case, then we know this plot. So VDS minus VGS minus VTH means you are operating in the triode region. So if your VDS is voltage between drain and the source, that is less than VGS minus VTH means you are operating in the triode region. Then VDS equal to VGS minus VTH. If both are equal, you are at the edge of the triode region. If you make this condition VDS greater than VGS minus VTH, if you can get this condition, then you are operating in the saturation region. So these are the 3 important biasing schemes in the MOS transistor. So you can decide your MOS transistor where to operate. If you want to operate as an amplifier, you have to operate in the saturation region here. If you want to operate in the saturation region, you have to make sure that your drain source voltage between drain and source must be greater than VGS minus VTH. So we are going to put in some values. So this is here 1 volt. Maybe I will connect here only 0.2 volt between drain and source. So 1 volt, definitely that is greater than threshold voltage. So this is on. Your MOS transistor is on. But then here, because this is 1 volt, so what is your VDS? VDS is 0.2 volt, and then that is definitely less than VGS minus VTH. So your VGS equal to 1 volt minus 0.5. So you are getting 0.5. Definitely 0.2 less than 0.5. So then in this condition, if you apply something like this, your VGS is higher, VGS minus VTH is higher than your VDS. If it is, this is the potential you are applying, then your MOS transistor is operating in the triode region here. You can decide by applying different voltages which point in the triode region. Then here if you connect 1 volt, and then if you connect here 0.5 volt, then you are at the edge of the triode region, because now VDS equal to 1 volt, VGS minus VTH, VDS equal to 0.5 volt, VGS minus VTH, VGS equal to 1 volt minus 0.5 volt, so 0.5 equal to 0.5, so VDS equal to VGS minus VTH, and here this one is operating at the edge of the triode region, so this point. We got one more case, that is equal to VDS greater than VGS minus VTH. So if you want to operate your MOS transistor in the saturation region, like you are making an amplifier, if that is the case, you should be providing this biasing. Your VDS should be greater than VGS minus VTH. In that case, what you will do is you will keep your gate voltage. See, in all the cases, what you have done is you kept it same, and then here it is 0.2, very small. VDS should be less than VGS minus VTH. Then here it is acting as a voltage dependent resistor. Because of this one, here you are getting a very good voltage dependent resistor in this region, in the triode region. Then at this point, edge of triode region. Then here 1 volt, and then we have to increase the VDS. I am going to connect 1.5 volt. So then we can check it. Your VDS, that is equal to 1.5 volt. Then VGS minus VTH, 1 volt minus 0.5, so 0.5 volt. So your 1.5 is definitely greater than 0.5. So this is operating in the saturation region, so this region. And then this voltage values, this type of biasing, VDS greater than VGS minus VTH, then only you can use it an amplifier. But then when you look at here, you can find out there is an issue. So when you have more drain voltage, this is 1.5 volt, and then, so what is the potential difference between gate and source at this point? So gate and drain, minus 0.5, means here the electric field is this direction, this direction, this direction. Maybe at this point, here the voltage equal to 1, and then it is going 0 like this. See, that is the reason now electron density, you can see the density is decreasing, because at this point, here it is 1 volt actually, around 1 volt, and then this region you don't have any electrons. Why you don't have the electrons? Because you don't have any voltage between gate and source here. It is a negative value, so you don't have any electrons here. So the electrons are ending here. But then there is a problem. When the electrons are not here, it can't attract, because here is 1 volt, here it is 1.5 volt. Electric field is other way around. But then the question is, you can see here is you are getting maximum current. How it is possible? So it is possible, why? Because here you are getting a gap. That gap is maybe in the order of nanometers. And then when you have nanometer gap, and then you got electric field, and then that electric field will be a very high value. So you got a potential voltage difference between these two. Here voltage is different, here voltage is different. That is a delta V. A small voltage difference between these 2 points. And then because the gap equal to nanometers, the electric field here is going to be very high, and then that electric field will help the electrons to move. That is the reason here the electrons are moving from this region to this region with the help of this electric field. That is a very large electric field. As the potential difference between drain and gate becomes more positive, that's what's happening here. the inversion layer beneath the interface starts to pinch off around the drain. So this is called a pinch off region. So it's called pinch off. That's the name, channel pinch off. So you don't have that inversion layer here. The electrons, you don't have actually, basically electrons are not accumulating here, but the electrons are moving across this barrier here, pinch off region. Electrons will come here and then move very fast to this region because of this electric field. When Vd minus Vg equal to Vth, the channel at drain totally pinches off. So that's the reason here, this gate voltage equal to this voltage. So 1 volt here is, this is also is almost 1 volt here at this point. At that point, see, channel at drain totally pinches off, and when Vd minus Vg greater than Vth, the channel length start to decrease. So what is happening is now your channel length is, previously your channel length is this much. So we calculate the channel length based on how long you got the electrons distribution. And then here the channel length is L, but then here the channel length is now L1, which is less than the L, because here you don't have any electrons. And then, so this is called the channel pinch off, that phenomena. But in the channel pinch off, then you can see the electrons are moving across this pinch off region, but you don't find any accumulated electrons here. The moving is from this electrons coming here, it will be moving very fast across this one because of the electric field. And then, so the electric field, maybe I can draw it. The electric field is very, very high in that region because you got a nanometer gap. See, something like this. So you got the channel pinch off is in a small region. So this is your gate, and then this is your gate, and then this is your insulating oxide layer, and then this is your source, and then this is your drain. Then you have connected some voltage here, and then maybe this is 1.5 volt, and then here you have connected 1 volt. So that is a, then what is happening is, so I already said this region, so drain, and then here the electron, so here what is happening is electron density is like this. So it's kind of exaggerated drawing, so electron density is disappearing because this is 1 volt, here also it is 1 volt. And then here 1.5 volt, here 1.5 volt, then here, see, electric field is this direction, 1 volt, like this, like this, like this. Here you don't have electric field between these 2 points because this is 1 volt, this is 1 volt. But from this point onwards, electric field is this direction because it's a negative charge. See, direction is like this. Here the direction is like this. At this point you don't have any direction because both the voltages are same. But then that's the reason you don't find any electron density here. But because this gap is in nanometers, and then here you got 1 volt, here you got 1.5 volt. So you got a voltage difference of delta V. And then your electric field equal to delta V divided by the separation, that is in nanometers, which is equal to delta V into 10 to the power of 9 order. That is volt per meter. So that is a very big electric field. And then that electric field, electrons comes here, then because of that this much big, 10 to the power of 9 order of volt per meter, that is electric field in this region. Then it will be quickly moving to this region. So that's the reason electrons are moving during the saturation, means in the saturation region, during the pinch off. When the pinch off happens, still the electrons are moving across this region. And then because if you don't know about the pinch off, you might be thinking, oh, okay, when you apply VDS greater than VGS minus VTH, you will not have any current here because you don't have the static, charge accumulation. Yes, you don't have the accumulation here, but because of the electric field here, the charge will be moving here. Dynamic charge you will find here, but you don't find any accumulated charge here. So this is called channel pinch off. The channel pinch off will reduce the actual length of your channel. See, that will reduce the actual length of your channel. Then now we are going to derive some expressions because in the case of BJT, we know that IC, which is equal to IS into exponential VB by VT, we know some expression relating your base emitter voltage to collector current. Then here you got a drain current, and then we got a gate voltage. So you can control the drain current using the gate voltage. But then we have to derive some expression. So what is the relationship between drain current and voltage between gate and source? Then now that's what we are going to derive it. So for that one, we are going to take a cross-section of a NMOS transistor, NMOS, because the channel is made of electrons here, because this is on a P substrate. And then W is the width of the gate. Then you can easily write the charge is equal to capacitance into voltage, Q equal to C into V. So charge means this charge, you got this gate, then you got a dielectric here, then you got a channel here. So the charge stored between this region, that is equal to Q into C, Q into V, Q equal to C into V, capacitance into voltage. Then if you are taking capacitance equal to W into COX, I can write it, because COX is the gate capacitance per unit area. So COX is the gate capacitance per unit area. Then I can write C equal to W into COX. Why I have written is I want to take into account this width of the channel in the calculation. That is the reason we are finding capacitance per unit area into how much area you have got. So if you write like that, instead of just write C, then we are taking into account the width of the channel. So for that we will take capacitance per unit area and then into your whatever the width you have got. So I will write C equal to W into COX. And V is the voltage difference between gate and the channel. So V is the voltage between gate and the channel, which is equal to VGS minus VTH, because we will take that as a minimum value, VGS minus VTH. Why? Because below VGS minus VTH there is no charge exist, because before that it is off. So we are going to find out the drain current when the MOS transistor is on. There is no point in finding out the drain current when VGS is less than VTH, because then your MOS is off. Then why do you want to find out drain current? You don't get any value. So what we are going, so our V is the voltage between gate and source. What we are taking is VGS minus VTH, because we want to make sure that your MOS transistor is in the operating mode, means in the on state. So channel charge density. Then we are going to find out how much charge density is here in the channel, which is equal to W into COX, which we already got it, capacitance, and Q equal to C into V. So we are putting this W into COX here, and then VGS minus VTH. That is a voltage we are assuming. Why? Because we want your NMOS transistor to be on. So VGS minus VTH. But then we already discussed this is not correct. Channel charge density, this equation is correct if you are getting a uniform distribution across this one, because your electron density, actually we are assuming this equation is correct if this one is a straight line up to here. But then because the electron charge density is decreasing towards the drain region, then we have to modify this equation to take into account that reduction. Because with no channel pinch off, if you don't consider channel pinch off, then this is the length, and then what is happening, this is the voltage distribution of the drain. Means here you got more voltage, and then the voltage is decreasing towards this region. Then you have to take into account what we will do is QX, means voltage charge stored, the channel charge density at a point X, which we can write it as W into COX into VGS minus VXC. I have written VX. VX is this VX minus VTH. So in order to understand, put Vx equal to 0. So Vx equal to 0 means Vx, what is the value of Vx here? That is equal to 0. And then at this point, your Vx is Vd at this point. So now we got the varying channel charge density using this equation when we add this Vx. So that is the reason we have added this Vx to take into account this slope. Now let X be a point along the channel from source to drain, and Vx is potential. Vx goes from 0 to Vd. See, Vx is a voltage. We are defining Vx, that is this Vx, that is varying from 0 to Vd. So we have to take into account that Vx here, then only you will get that slope here, the slope in the channel charge density. And then we are not calculating for channel pinch off. Our assumption is here there is no pinch off. Now what we are trying to do is we are going to visualize in the 3D. In the 3D, we are assuming some charges here, that is in a cubical manner. So that is this called V meters or L meters, delta L meters. You are having some charges that is moving across anywhere this region to this region. and then charges, and then what we are happening is the electrons are moving from here to here, so that your current direction is from here to here, and then this much charge is moving. See, a cube of charge, we are taking a cube of charge is moving across this channel. Then we can write charge enclosed in V meters or L meters per second, that is equal to Q into velocity. So why I have taken Q into velocity is like, what is velocity? Velocity equal to dx by dt, displacement by time. But then for 1 second, your velocity equal to change in the displacement. You know what I meant? So then charge enclosed in delta x meters in 1 second, that is equal to V meters, velocity meters, means the idea is this one, V, velocity equal to dx by dt. You know that expression, that's a basic equation. But for 1 second, your velocity V equal to dx, because dt equal to 1 second. Then I can write x meters, dx meters, I can say V meters per second. So that is the reason charge enclosed in V meters or dx meters in 1 second, that is equal to Q into delta x, but then delta x equal to velocity, because it's for 1 second. So I can write Q into velocity. Then current equal to, so charge enclosed in V meters, because that is per second. So charge per second, that is actually your current. I equal to Q into, instead of velocity, if you are putting dx by dt. And then for 1 second, so your charge into velocity, that is equal to your current. Then velocity, you know the standard expression, that is equal to minus mobility of electrons into electric field. So whatever the electric field you have got here and the mobility of electrons. So then you can substitute. Then ID, that is a drain current, which is equal to W into COX, the previous expression. See, this expression. And then here now what we are going to do is, we got this already expression for the QX. And then now we got the expression for the current. So we are substituting ID equal to, that is a drain current, W into COX, VGS minus VX minus VTH, mu n into dVx by dx. Because this electric field, that is equal to potential by separation between the points. So dV by dx, that is electric field. Then we can integrate 0 to L, that is your channel length. Because this ID into dx is here, it can come here. So ID into dx, the channel is varying from 0 to L. And then the potential is varying from 0 to VDS. Because here voltage equal to 0, and then here it is VDS. So that is the reason 0 to VDS, your voltage is increasing, and then we can integrate. So when you integrate, what you are getting is just the integration. For the linear region, your ID equal to mu COX by L VGS minus VTH into VDS minus V square ds by 2. So this is the expression for drain current in the linear region. Again, you don't have to study the derivation. I have just shown you the derivation. So this is expression for drain current in the linear region. So this is expression. So if you are operating your MOS transistor in the linear region, this is expression for the current, drain current. Then if you want a channel pinch off, the condition is VDS should be greater than or equal to VGS minus VTH. If I put in VDS equal to VGS minus VTH, that is this point, then I can find out what is the drain current in the saturation region. You can put in these values, VDS equal to VGS minus VTH. So then when you put in that value, because instead of VDS you put in VGS minus VTH, here also you put VGS minus VTH here, then you can solve it, and then just rearranging, you get ID maximum, that is the drain current maximum, because this current half mu n COX W by L VGS minus VTH the whole square. See, that's the current we are getting. So if you recall the other equation, IC equal to IS exponential VB by VT, but then here drain current equal to, you don't have any exponential term. It's VGS is there, that is equivalent of your VB, but then you don't have this VTH for the MOS transistor. So ID, that is equal to half mu n mobility of electrons, capacitance per unit length, width of the channel, length of the channel, VGS minus VTH the whole square. For the BJT, you don't have any of these width, length in your equation. given threshold, and then we don't have the exponential relationship here. So that is the current in the saturation region. Then from this one you can see there is a parabolic relationship. See, ID proportional to Vg minus Vth the whole square. So there is a parabolic relationship between Vgs and ID, not an exponential relationship. So that is the reason parabolic ID VDS relationship. So you can see, you can plot ID and then you can plot VDS. Then this point, that is called half mu n COX W by L VGS minus VTH the whole square. So you got a parabolic relationship, and then this point is VGS minus VTH when you plot it. Well, obviously it is not coming down, it is going this way, that is parabolic, and then it will be going straight. But up to this point, that's a parabolic. That's the reason you got this equation, the maximum value. And then this again, the slope is different for different VGS minus VTH. So VGS1 minus VTH, you will be getting like something like this slope, and then in the triode region. And then if you increase the VGS value, then you are getting another slope. Pretty much similar to BJT, but here I have shown only until the triode point. So it will never come back like this and become zero. It will go like this for the MOS transistor, like this. So what we have found is ID that is proportional to VGS minus VTH. So that's the reason we are getting a curve something like this. By keeping Vg constant and varying VDS, we obtain parabolic relationship. So how do you get this parabolic? By keeping, you can keep Vg constant and then you vary the VDS. Then you will find this kind of parabolic relationship when you measure it. The maximum current occurs when VDS equals VGS minus VTH. The maximum current, that is this point. So find the linear resistance. So that is a group work. Now what I want to find is, I'm going to take this triode region. In the triode region, the entire region is not linear. Only this much part is linear, because here it's not obeying Ohm's law because there is a curvature. But if you take this part, somewhere this part, then it's a linear region. The slope, you see the line is straight. That is called ohmic region. So I'm going to take that region and then zoom in. When I take only this region, that's what you are getting. And then I'm going to take only a small region even below this one, means some point somewhere here. And then again, if you zoom in, you will see straight line. See, there is no curvature. So this points here, this region is an ohmic region, because you are getting a straight line, it is obeying the Ohm's law. Then we can use it as a voltage dependent resistor, which I already discussed. Now what we are going to find out is, I'm going to find out what is the resistance value from this equation, because here you got ID, then you got VDS. So then we can find out what is the resistance of the channel, because previously we know that is a voltage dependent resistor, but then we don't know the value, what equation we can use. But now because we got ID and then we got VGS, VDS, all these things in the equation, now we can find out what is ID by VDS or delta ID by delta VDS. If you find out, you are getting the resistance across this channel in terms of width, length, mobility, capacitance per unit length, VGS, so all the parameters are already taken into account. So when you find out, it is easy. So now what we are going to do is, VDS is much less than 2 times VGS minus VTH. So why we are taking this one is so that your point is somewhere here, very close to this point. That is a linear region. That's what we wanted. So if you put that condition, your ID equal to mu n COX W by L VGS minus VTH in the VDS. So that is a drain current. Otherwise also you can find out, you can just differentiate delta ID by delta VDS. So if you do that one, again you get the same expression. And then you can find out R on. So what is the on resistance? The on resistance is, you got ID, then you got VDS. So VDS divided by ID, that is your on resistance of the channel. So on resistance of the channel is 1 by mu n COX W by L VGS minus VTH. So now we found out what is the on resistance of the channel. At small VDS, the transistor can be viewed as a resistor, a voltage dependent resistor, with the resistance depending upon the gate voltage, which we already discussed. It finds application as an electronic switch. So then here, if you look at this one, this got a very good application. Why? Because your own resistance, this is the value of own resistance. Then when your VTH is, when your VGS equal to VTH, what is the own resistance? So if you put, initially what happens is you got this equation and then you got this MOS transistor. Initially VGS equal to 0 and then it will not be on because you need a threshold voltage VTH to switch it on. But my question is, when your VGS equal to VTH, then you are just turning on the MOS transistor. Then at that time, you know what is the on resistance equal to infinity, because VGS equal to VTH and then this is equal to 0 and then your own resistance equal to infinity. So means you can use as a very good switch. So if you got infinite resistance means you can act as a very good switch. That is a problem with the BJT. So if you want BJT, even if you switch it off, still there will be some current. Your VB, so you can control your VB, but then even if you put a small VB like 0.7 is a cutoff, maybe VB requirement is 0.7, you connect 0.6, but still you will get some leakage current in the BJT. And then for MOS, you don't have that type of leakage current. The best way to understand this one is using this equation, R on, which is equal to 1 by mu n COX W by L VGS minus VTH. VGS is equal to 0 means your transistor, MOS transistor is kind of off. But then you increase the VGS, when the VGS is just equal to VTH, you can see the resistance is equal to big value. So that's the reason you can use it as a switch. It finds application as electronic switch because of this reason. Now we studied about MOS. Now I am going to ask another question. You have got a base current for BJT, IB. So what is the, here what is the gate current for MOS? So what is the gate current? Okay, somebody already said 0. Why? Because it's 0. Why? Because here you can see you are applying some voltage here, but then because of this dielectric material, no current can pass through. So the current, gate current equal to 0 for MOS. Then what is the input impedance? Infinity. So the MOS transistor got another advantage, the input impedance equal to infinity, very high value. In the real MOS, if you buy a MOS JFET or something, then you will find in the data sheet gate current equal to picoamps, 10 to the power of minus 12 amps, means very, very small, means close to 0. And then that's the reason in the MOS transistor, input impedance equal to infinity. So that is very good, so that when you draw your small signal, your R pi equal to infinity. So you don't have to draw that region, input region. Then MOSFET as resistors in CMOS design. Then here we already said you can use as a resistor, voltage dependent resistor if you are operating in this region. Also you can use as a switch because of this property. Then the next question then people might ask you, no, it's good. Then where are you going to use it? In the chip, it got a very good application. When you design actually chip, then MOSFET, most of the time in your laptop, in your mobile phone, everywhere in the IC, the MOSFET is used as a resistor actually. Why? Because real resistance versus MOSFET resistance. What is advantage? Smaller in area than actual resistors. If you want to put in the resistor, a real resistor in the chip, the problem is you need more area. If you are bigger value, then you need more area. Because resistance equal to R equal to rho into L by A, the area. Then if you want to put in more resistor, if you want a bigger value in your chip, you need a bigger space. But you can design a small resistance, means small area resistance with higher value using MOS. Another one is can pass a large current through a large resistance without a large voltage drop. Means I got some resistance, then this resistance will decide how much current it can pass because there is a drop. But then I can decide, I can reduce the voltage drop across this resistance and pass more current. See, if I use MOS, because MOS is an active device. This is an example. So this is a current, this is a voltage. Then I am going to connect a standard resistor. I'm very happy to put a standard resistor in the chip at the cost of increasing the area. If I do that one, so this is the IV characteristics for my resistor, because that's a linear, see, that is a line. But then if I pass 10 microamps across the resistor, so I put an ordinary resistor in the chip, and then if I pass 10 microamps and then the value of the resistance is 100 kilo ohm, then the voltage drop across that resistor equal to 1 volt, because 10 microamps into 1 volt. But if I use a MOS with suitable biasing in the triode region, I can pass 100 microamps and then the drop will be only 1 volt. You know what I meant? Even here I can see, because in the ordinary resistor, if you are using an ordinary resistor, if you are passing 100 microamps, you will have 10 volt drop across that resistor. But then you can reduce that drop to 1 volt but still pass 100 microamps. You know what I meant? Yeah, so that is a advantage if you are using a MOS as a resistor instead of real resistors. So this graph is a very good graph explaining the concept. So MOSFET as a resistors in CMOS design. In the CMOS design, because of these characteristics, we can design MOS as a resistor, voltage dependent resistor. Then you can get a different resistance value using different voltages at the gate. And then when you design a chip, you will be designing something like this. You want to design this resistor, then you will be using a particular voltage, and then this is A, this is B, and then that is a point. Then when you plot the characteristics, see, this is a different slope. I have plotted only the linear region or triode region. So different voltages, you are getting different slopes in the triode region. So different slopes corresponds to different resistor values. So you can apply different voltages like 7 volt, 8 volt, 9 volt, 10 volt, then the slope is different. Slope is different means you are getting different resistance value. So you can tune to any resistance value. Then if you want some other higher value in the chip, they will be designing something like this. They connect a voltage here, then use one MOS, then you can connect another MOS in parallel. If one MOS, if you can't get enough tuning with this much voltage range, you can connect maybe 2 in parallel, 3 in parallel. That's how in the chip, when you use the chip, when you design chip, that's what people use. They use MOS as a resistor instead of actual resistor in the chip, and then different values are obtained by connecting different gate voltages. And then also you can combine in different topologies like this. Yes, at small VDS, the transistor can be viewed as a resistor with the resistance depending on the gate voltage. So different regions of operation. The MOS got mainly 2 different regions. One is a triode region, another one is a saturation region. And then in the triode region, this is a distribution of the electron density. In the saturation region, you are getting a pinch off. When the potential difference between gate and drain is greater than VTH, the MOSFET is in the triode region. VDS less than VGS minus VTH. When the potential difference between gate and drain becomes equal to or less than VTH, the MOSFET enters the saturation region. And then, so because of that one, we will get a quantity called channel length modulation. So without channel length modulation, this is your current, drain current. Then there is no channel length modulation, means your channel length is same. But when you have channel length modulation, what is happening is because of the pinch off, when you are operating in the active region, your channel length is less by delta L. Now this is your channel length L1. And then that is called, so we have to take into account that delta L, the variation, then that is called channel length modulation. So when you don't have channel length modulation, you are getting straight line. When you have channel length modulation, this pinch off, when you take into account this pinch off, your current will slightly increase like this. So then that is the equivalent of Early effect in MOS. So channel length modulation or the pinch off part, the pinch off is creating something equivalent of Early effect in the case of MOS. So when you take into account the channel length modulation, then this drain current we will be adding one more term, 1 plus lambda into VDS, like we do for the collector current. And then this ID lambda, so we are taking into account lambda is the channel length modulation. So that is equivalent of Early effect in the BJT. Lambda is the channel. Original observation that the current is constant in the saturation region is not quite correct, like straight line. The end point of the channel actually moves towards the source as Vd increasing Id. Because of this pinch off region only, we are getting channel length modulation. We are getting an effect that is similar to Early effect for the BJT. I think maybe I'll stop here and continue in the next lecture.